Welcome back for more so we can talk about how mature bone continues to grow and remodel itself. Infant bones are very soft and pliable because of incomplete ossification at birth. But ossification does not end at birth, and bones grow in two directions. They grow in length and they grow in width. So in this way, we have to have when bones grow in length, they have to ossify from an area between the diaphysis and the epiphysis of the bone. That way the growth does not interfere with articulation between any two bones. So to understand growth in length, we have to return to the epiphyseal plate. From infancy throughout adolescence, the epiphyseal plate is present at one or both ends of a long bone, specifically at the junction between the epiphysis and the diaphysis in an area called the metaphysis. When it comes to bone growth and remodeling, your skeleton is replaced about every 7 years. So this process continues throughout your life. And your bones are constantly being remodeled and they're constantly responding to stress. So as the bones get longer or elongation, we are going to focus in on that epiphyseal plate that we talked about in our last lecture. This is going to serve as the growth zone. And there is a transitional zone on each side of the epiphyseal plate where cartilage is going to be replaced by bone. So this is where the epiphysis meets the diaphysis called the metaphysis. And the structure of the metaphysis is going to change and it will correlate or correspond to the steps of the cartilage being replaced by bone. We've got 5 layers and they're going to go from the epiphysis side to the diaphysis side. We'll have the zone of reserve cartilage, and then we'll have the zone of cell proliferation, the zone of cell hypertrophy, the zone of calcification, and the zone of bone deposition. On x-rays, it appears as a translucent or kind of see-through line across the end of a bone since it has not yet ossified. The epiphyseal plate is a region of transition going from cartilage to bone and functions as a growth zone where the bones can elongate. So growth here is going to be responsible for a person's increase in height. And that way, the bone growth is not going to interfere with the articulation of the bones at the joint. The epiphyseal plate consists of a typical hyaline cartilage in the middle with a transitional zone on each side where cartilage is being replaced by bone. So recall from Unit 2 that when we went over histology, the hyaline cartilage is made by chondroblasts, and there's very, very few collagen fibers. And those chondroblasts have trapped themselves in a lacuna, right? And so that's those little avocado shapes. Those are the chondroblasts in the lacuna, typical hyaline cartilage. So the transitional zone that is facing each marrow cavity is called the metaphysis. The cartilage is the blue region, And the metaphysis is the violet region. So if we're looking right here, that's what we're referring to right here, right? This blue is that hyaline cartilage. And then you have the purple region that is the violet and part of the metaphysis. So that's that transitional zone. And this illustration is showing a cross section of bone and cartilage and those blood vessels. So the center portion of the cartilage is labeled zone 1, right? So right here, zone 1. And that's what we're going to start to zoom in. And the area below, right, is going to be zone 5. So on this larger diagram, right, this area is zone 1. So that's going to be the blue region. In here, the cartilage, hyaline cartilage. And then down here is going to be the zone 5, where we have the bone. So the micrograph is showing the region above and below the cartilage. The right side of the micrograph is going to be colored based on the types of zones. Zone 1 is the zone of reserve cartilage, and you will see the typical histology that's of resting hyaline cartilage with those little lacunas. Zone 2, that's going to be this area down below here, so it's highlighted in blue on the side, but it does continue to this area here also. That is the zone of cell proliferation. This is where chondrocytes are lining up in rows, and I hope you can kind of see those rows. Of course, they're not perfect, but they're rows. And that's where the chondrocytes are flattened in those lacunae. Zone 3 is this green zone here. This zone, and carrying on, is the zone of cell hypertrophy. This is where there is an enlargement of the chondrocytes and the lacuna walls are starting to thin, right? And so that's why we're going to see less of that stain. So we can see that it's starting to kind of widen up in that area. And then zone 4 is where we're going to start to see calcification of the cartilage matrix between the columns of lacuna. So we're going to start having minerals being deposited here, and we begin to calcify, turning that cartilage into bone. And zone 5 is the zone of bone deposition. So that is where the lacuna walls are going to completely break down, and now the lacuna are open channels, which is going to lead to the death of those chondrocytes and the deposition of bone from osteoblasts. And this is going to start to form the trabeculae and spongy bone, or the trabeculae of spongy bone. So you can start to see those little beams of trabeculae beginning to form here. Zone 1, if we go back up to zone 1, where we're in the blue, so here we've got the cartilage, the zone of reserve cartilage. This region is going to be furthest from the marrow cavity. And once again, it consists of a typical hyaline cartilage with those resting chondrocytes. And it's not showing any sign of transformation into bone. In the next zone, you should start to notice that those cells are beginning to look a little squished and forming these lines. So we are now a little closer to the marrow cavity. The chondrocytes have multiplied and arranged themselves into these longitudinal columns of these flattened lacuna. And then we're going to start to see the breakdown of lacuna here in the zone of cell hypertrophy. Okay. So that's where the chondrocytes are going to stop multiplying and they're going to begin to hypertrophy. And if we break down that word, it means to enlarge, much like they do in the primary ossification center of the fetus. The walls of the matrix between the lacuna become very, very thin in this zone. And then we're going to move into the zone of calcification. So now we're going into the bone marrow. And this is where the minerals are going to start to get deposited in the matrix in between the columns of lacuna, and that is going to calcify the cartilage. These aren't the permanent mineral deposits of bone, just only a temporary support for the cartilage that would otherwise soon be weakened by the breakdown of those enlarged lacuna, right? The lacuna won't be able to support the weight and it's going to break. So then we have the zone of bone deposition, which is zone 5 here. So that's closest to the bone marrow cavity. This zone of bone deposition, within each of the columns or the walls between the lacuna, they have broken down, and because now there's no wall, they are going to expose the chondrocytes inside to the osteoblasts, and they're going to die. So this is going to start to convert each column into a longitudinal channel. So it's the clear space in this image that you see. It is immediately invaded by blood vessels and marrow from the marrow cavity. The osteoblasts are going to line up along the walls of these channels and start depositing concentric lamellae of matrix, while the osteoclasts are going to dissolve the temporarily calcified cartilage. And this process of bone deposition in zone 5 creates a region of spongy bone at the end of the marrow cavity facing the metaphysis. This spongy bone remains for life, although with extensive lifelong remodeling. You get a new skeleton every 7 years. Around the perimeter of the marrow cavity, continuing ossification is going to convert this spongy bone to compact bone. Osteoblasts lining the channels deposit layer after layer of bone matrix, so the channel grows narrower and narrower. These layers become concentric lamellae of an osteon. Finally, only a slender channel is going to persist in the central canal of a new osteon. So the osteoblasts trapped inside the matrix are going to mature and become osteocytes that will maintain the bone matrix. And they're actually going to be connected to one another. So the structure that they're going to reside in is also called a lacuna, and they will have processes from their cells going out, and it will go through the structure called the canaliculi, so that way the processes of these cells can reach out and they can communicate with one another. If you've ever asked or thought, like, how does a child grow, or how does an adolescent grow in height? I know sometimes I look at my kids and I'm like, oh my gosh, how did you get so big? Well, chondrocytes multiply in zone 2 and hypertrophy in zone 3 continually. And as they're doing that, it will push the zone of reserve cartilage, zone 1, up and towards the ends of the bone. And so this is going to elongate the diaphysis, or the shaft of the long bone. In the lower limbs, this process causes a person to grow in height, while the bones of the upper limb form those body proportions. And they usually
form pretty proportionately. Even though we're all very different, our body proportions are actually pretty similar. For example, your femur makes up about 25% of your body height. So bone elongation and this growth is really just a result of cartilage growth. Cartilage growth from within the bone and within the specific epiphyseal plate. The cartilage in that zone 1 is going to grow by multiplication of chondrocytes and the deposition of new matrix in the interior, and that is called interstitial growth. The most common form of dwarfism actually results from a failure of this cartilage growth in long bones. And in the late teens to early 20s, all cartilage of the epiphyseal plate starts to become depleted, and the primary and secondary marrow cavities will then unite and form one cavity. The junction region where they meet is going to be filled with spongy bone, and the site of the original epiphyseal plate will be marked with a line of just slightly denser spongy bone that is then called the epiphyseal line. When the epiphyseal plate is depleted, we say that the epiphyses have closed because there's no gap between the epiphysis and the diaphysis that is visible on an X-ray. Once the epiphyses have all closed in the lower limbs, the person will no longer grow taller. And the epiphyseal plates close at different ages in different bones and in different regions of the same bone. The process and the rates of the elongation and epiphyseal closure are going to be influenced by growth hormone and sex steroids. The state of closure in various bones of a young adult skeleton is often used in forensic science to estimate an individual's bone age at death, so we can determine approximately how old that person was. But this is also why we are very iffy and cautious when it comes to the use of steroid drugs, especially in young individuals and teens, because those steroids tend to increase the osteoblast activity. And so the osteoblast will close the epiphyseal plate too soon. And once that plate is closed, it is closed and no more growth is happening. And so these steroids can influence that, and that's why we don't like young adults to be on steroids for a long period of time. This is also influenced by other hormones, and everybody's a little bit different. So some individuals, this can happen to very rapidly, while others, it will take longer. Achondroplastic dwarfism is where the long bones stop growing in childhood. So this is a failure of cartilage growth within the metaphysis, and it causes there to be a normal torso, but the limbs are shortened. Typically, this is caused by a mutation that is a dominant mutation, so only one copy of the allele is needed for the dwarfism. In contrast, pituitary dwarfism is where there is a lack in growth hormone. So typically the person is normal in body proportion, but they'll just be really short in nature. While bones are increasing in length, they are also increasing in diameter. Growth in diameter can continue even after longitudinal growth stops. This is called appositional growth. The osteoclasts will work to break bone down, resorb old bone that lines the marrow cavity, and at the same time, we're going to have osteoblasts by intramembranous ossification producing new bone tissue underneath the periosteum, so on the other side of the bone, making the bone wider. But if we continue to make the bone wider and it just gets thicker and thicker, that will make our bones really dense and really, really heavy. So we're gonna have to have the medullary or marrow cavity hollowed out and um, increased, or that endosteum kind of eroded as the bone is getting thicker. That way the ratio stays about the same. So the erosion of old bone along the medullary or marrow cavity and the deposition of new bone beneath the periosteum not only increases the diameter of the diaphysis, but it also will increase the diameter of that cavity. And a lot of times that is referred to as remodeling. So as the osteoblasts are building this new bone, they're going to deposit that osteoid tissue, so the collagen fibers, and they're going to then take the calcium and hydroxyapatite salts and incorporate that into that osteoid. And as they do that, they are calcifying that matrix. And when they do this, they are laying them down in specific directions or patterns. And it's going to be in layers that are parallel to the surface, and it forms circumferential lamellae. And then they are trapped in that calcified tissue in a little lacuna, and they will differentiate and turn into osteoblasts. Bone renewal continues after birth and into adulthood. This bone remodeling is the replacement of old bone tissue by new tissue, and it involves the process of bone deposition or bone production that is done by osteoblasts and bone resorption that is done by osteoclasts. Normal bone requires some vitamins and minerals, but there are also hormones like the parathyroid hormone and calcitonin that are also required for this proper bone growth and maintenance of the bone. But there are also some factors that that influence this bone remodeling. And it's biomechanical stress that is placed on the bones themselves. So the more stress you put on your bones, being a living tissue, will respond to that stress, and they will build new bone along those lines of stress. So if you increase mechanical stress, like by doing exercise or running, jumping jacks, things that stress your bones, you will develop stronger bones in response, right? You will have many bony processes that start to grow. If you have a more sedative lifestyle and you do not put mechanical stress on your bones, well, that is actually going to have the opposite effect. So you will actually increase osteoclast activity and decrease osteoblast activity, which will lead to weaker trabeculae and weaker bones. But by putting stress on the bones, that will stimulate the osteoblast activity to build bone along those lines of stress, and it will inhibit the osteoclast activity. So that way your bones can resist that mechanical pressure being put on them. We'll end this one. See you next time.